Hello everyone and welcome back. So today we are going to be looking at some of the basic applications of integrals. We are going to do more applications with integrals both in Calculus 2 and in your major courses that require calculus, but we're going to be doing some of the basic applications of integrals in this video. So just to clarify the similarities and differences of definite versus indefinite integrals. They are both types of integrals and they have a lot of similarities, but they have a lot of differences. So definite integrals contain bounds on both the top and the bottom. So a definite integral gives you the exact net area under a curve on the closed interval a to b. So that means definite integrals are numeric, and they can be evaluated, and they are equal to a single numeric value. Now, because definite integrals are going to involve you taking the antiderivative, evaluating at the top, minus the antiderivative evaluated at the bottom, they do not require a plus c. Now, indefinite integrals are unbounded. Indefinite integrals are just the general antiderivative. They give you a family of functions that all have the same derivative. Indefinite integrals do require a plus c. Indefinite integrals do not give you a value of a specific area under a curve. They are just the general antiderivative, and that is it. Now, both of these types of integrals use antiderivatives. The definite integral calculates the antiderivative's value over a given interval. The indefinite integral just gives you the general antiderivative, a family of functions that all have the given derivative. Only with an initial condition can you get a specific function. If you need a refresher on what that means, I encourage you to go back and review the section on antiderivatives and the indefinite integral. So, first application of integrals is what is called average value. You might remember that to take an average or mean, all you have to do is add together all the data and divide it by how many there are. So since integrals are technically an infinite sum, they are used to find the average value of a function. And when that function stands for something applied to real life, it will find the average value of whatever that function represents. So the how many there are comes from n, which is the number of subintervals. So basically, the average value is going to boil down to this. You will add them all together and divide by how many there are. And as the number of subintervals approaches infinity, that means this Riemann sum is going to become the definite integral. So this definite integral, which is an infinite sum, means add together all of the accumulated values and divide by the size of the interval, or times 1 over b minus a. So this is the average value of a function. It is denoted with the notation f bar. That bar over the f means just an average. So the average of the function f is going to be the integral from a to b of f of x dx times 1 over the size of the interval, b minus a. So for example, let's say that a hiking trail has elevation that is given by f of x equals 60x cubed minus 650x squared plus 1200x plus 4500. And f is measured in feet above sea level, and x represents the horizontal distance along the trail, and x is only between 0 and 5 miles. So x is a closed interval from mile marker 0 to mile marker 5. And we're going to find the average elevation of the trail. Now, since f of x stands for the elevation of the trail, if we find the average value of f of x, we will find the average elevation since f stands for elevation. So I'm going to set up my average value. So f bar is equal to 1 over b minus a times the integral from a to b of f of x dx. The size of our interval in this case is from 0 to 5, because the trail is only 5 miles long. So 1 over the b is 5, the a is 0, so 1 over 5 minus 0, times the integral from 0 to 5 of my f of x, which is 60x cubed, minus 650x squared, plus 1200x, plus 4500, dx. Now you can either evaluate this definite integral by hand or using a calculator. I do have a separate video on how to evaluate definite integrals on a TI-84. It is under the how-tos of graphing calculator playlist on my YouTube channel. So go watch that separate video if you do not know how to evaluate this on a calculator. Or you can easily find the antiderivative using power rule and then just plug in your bounds 5 and 0. But do not forget that you do need to multiply it by 1/5 or divided by 5. You should get approximately 3,960, somewhere in that ballpark. Now what that means in the context of the problem is that the average trail elevation above sea level is 3,960 feet. Remember, that is an average elevation. So there were some parts on that trail that were higher than this. There were some parts on that trail that were lower than this. But do you think that there was probably at least one mile marker that had an elevation of exactly 3,960 feet? Probably. Probably somewhere along that trail there was some mile that had this as an exact elevation. That should sound like the mean value theorem because it is. There is a mean value theorem for integrals. Now you might remember the mean value theorem for derivatives of, several videos ago, that there is at least one value on a closed interval if the function is continuous and differentiable, such that the function equals such as the derivative equals its average rate of change. The mean value theorem for integrals is somewhat similar. What it basically means is that there is some point C in a closed interval a to b such that the original function evaluated at C equals its average value. So in the context of that hiking trail, that means there was at least 1 mile marker between 0 and 5 where the exact elevation f of x was exactly equal to its average value, 3,960 feet. So what we're going to do for this next one is we're going to find the point or points on the interval 0 to 1 on which this function equals its average value. So this function is a polynomial, it's continuous, it's differentiable, and it's integrable. There is no product rule for integrals, so I do need to distribute that 2x before I do any integrating, so that will give us 2x minus 2x squared. So we're finding the points where this original function f of x equals its average value on the interval 0 to 1. So let's actually find its average value on this interval. So average value f bar is going to equal 1 over b1 minus a0 times the integral from 0 to 1 of 2x minus 2x squared. Now you can either evaluate this by hand or you can use a graphing calculator. As a general rule, unless the problem specifically tells you that you need to do a definite integral by hand, you can use a graphing calculator, but whichever, you get an average value of 1/3. So we are finding the values of x where the original function f of x is equal to its average value, 1/3. The mean value theorem for integrals guarantees that there is at least one value for x on this interval 0 to 1 where the original function f of x equals 1/3. So we're going to set the f of x to x minus 2x squared equal to 1/3. This is a quadratic, so I'm going to make the quadratic equal 0 by moving all of the terms onto one side. And I'm going to rearrange this so that the x squared term is first. So I have negative 2x squared plus 2, let's try that again, negative 2x squared plus 2x minus 1/3 equals 0. Now you have a couple of different choices. You can either use quadratic formula for this and solve for x. You should get 2x values. Or you can type in negative 2x squared plus 2x minus 1/3 into a graphing calculator and find the x-intercepts where it equals 0. You should get 2x values. So either quadratic formula or on a graphing calculator, you should get x equals 0.211 approximately, and x is approximately equal to 0.789. So those are the 2 points on this interval where this function f of x is exactly equal to its average value, 1/3. Now, the biggest application of integrals that we're going to cover in this class, and this is going to be a big focus on other classes that use integrals, is net change. So we started off this whole integral chapter with the car example, traveling at a constant speed of 75 miles for 2 hours. An integral is an accumulated amount of change. So if f prime is the rate of change of a quantity f of x, then the definite integral of f prime gives the total change or net change. So this is super generic because these functions, don't have to stand for moving cars. They can stand for any quantity that is changing. But the net change of a function f of x over a given interval a to b is the definite integral from a to b of its derivative, which would be, f of b minus f of a. Biggest application of this is in particle motion or in any one-dimensional motion problem. We're thinking position, velocity, acceleration. So the net change represents the total net change of displacement of an object in motion. If you have an object that is moving back and forth, let's say something that's moving left and right repeatedly, it'll count the movements right as positive and it will count the movements left as negative. So the total net change will be the net change in displacement and will count any movements left or down as negatives. So just taking the definite integral counts movements backwards as negative values. So this is important. The definite integral from a to b of velocity v of t dt gives you the total displacement. It will give you the total net displacement because the total net change is just the integral of the derivative. Since velocity is the derivative of position, if you take its integral over a closed interval, you will get the total net displacement of the position function. What that will do is it will take any movements backward into account as negative values. Now, if you don't care about direction and you just want total distance traveled does not care about whether it's moving backwards or forwards. It just cares about, is it moving at all? So if you want to find the total distance traveled, you have to take the integral of the absolute value of velocity. So the total distance traveled on a closed interval a to b is going to be the integral from a to b of the absolute value of v of t dt. So let's say that the velocity in feet per second of a particle moving along a line is given by this function v of t, where t is the time measured in seconds. So we're going to do two different things here. For part A, we're going to look at what is the total net displacement of the particle on the interval 1 to 5. So if you want to find the total displacement, that means you do care about direction and you do care about any negative directions counting as negatives. So that's just going to be a straight integral from 1 to 5 of our v of t, which is t cubed minus 10t squared plus 29t minus 20 dt. So you can go ahead and evaluate this on a graphing calculator if you wish. You should get somewhere in the ballpark of a 10.67. And since this is, would be in whatever the original position was in units, so if velocity is in feet per second, that means position was just in feet. So the total net displacement is 10.67 feet. Now keep in mind that this is possibly also moving backwards and forwards and taking any movements backward into account as negatives. Just a straight definite integral of velocity will always give you net displacement. So then for part B, if you're looking at the total distance traveled, that means you don't care about direction. All you care about is that was there any sort of movement at all. So if you're looking at total distance traveled, what you are going to be looking at is the definite integral of the absolute value of velocity. So we're going to be taking the definite integral from 1 to 5 of the absolute value of t cubed minus 10t squared plus 29t minus 20 dt. Now, if you don't remember where absolute value is on your graphing calculators, it is actually under the math option. If you scroll over to numbers, or num, the second option over, it is the first option, ABS. Now, some of the newer calculators will actually put this in as an absolute value. Other calculators will just have, ABS with parentheses. Those are the older ones, the TI-84, the TI-83s, older TI-84s, and so on. But just remember that you do need parentheses around the absolute value, so just make sure that the entire velocity function is encapsulated in that absolute value. You should get an integral of 11.83, and this is going to be in feet. So the total distance traveled, ignoring the fact that movements backward are negatives, making all those negative movements into positives, the total distance traveled, regardless of direction, is 11.83 feet. So for this next one, for t on a closed interval 0 to 6, let's say a particle is moving along the x-axis and it's moving back and forth along the x-axis. The particle's position you don't exactly need, but you do have the velocity function v of t is equal to 2 times the sine of e to the t over 4 plus 1. We don't need the acceleration. I stole this problem from something else, so you don't really need this part. So what we're going to do is we're going to find the average velocity of the particle on the interval from 0 to 6. So this is the velocity function. If you find its average value, what you will find is the average velocity. So to find average velocity, what we're going to do is we're going to take the average value of v of t. So average value is going to be 1 over b, which is 6, minus a, which is 0. Times the definite integral from 0 to 6 of my velocity function to sine of e to the power of t over 4 plus 1 dt. Now this one you absolutely need to evaluate on a graphing calculator because I did not give you instructions on how to do this by hand. So evaluating this on a graphing calculator, you should get approximately 1.949. Again, I have a separate video on how to evaluate definite integrals on a calculator, so go watch that if you need a refresher. So that is the average velocity, the average value of the velocity function. Now for the next one, we're going to find the total distance traveled by the particle from t equals 0 to t equals 6. Remember, total distance traveled does not care about direction. So you would need to make any negative directions count as positives. So we're going to be taking the integral of the absolute value of velocity. So total distance traveled is going to be the integral from 0 to 6 of the absolute value of 2 times the sine of e to the t over 4 plus 1 dt. Remember, you do need parentheses around that absolute value. The entire velocity function, including the plus 1, does need to be around the absolute value. And you should get approximately 12.573 when you evaluate this on a graphing calculator. So this is all that we're going to be doing for applications of integrals in this class. For the next video, we're going to be looking at some more integration techniques. You're going to be doing a lot more integration techniques in Calc 2, but we're going to do one major one in this class to kind of finish up the course. So thank you all very much for watching, and I will see you in the next video.